So, hey, what's up? In this video, we're going to do a simple proof to show a subset is a subset of a group. Here, H proof H is equal to 2Z. 2Z. H is a subgroup. H is all of the multiples of 2. So every element of H looks like 2 times n. Looks like H 2 times n, where is an n is an integer. And then our G here is going to be the set of the integers, and the operation here is just addition. So plus equals addition. So subgroup of a group is a subset that is also a group under the same operation. However, there is a theorem that we can use in this proof. So we say that H, and I'm going to use subgroup notation. I think this is the subgroup notations. So H is a subgroup of G. Uh, if there are three conditions, the first condition is that H is is not empty. H is not empty. So the first condition is H is H is not empty. H is not empty, and second is H is closed under the the group operation. The group operation. So what does that mean? That it means that for all x and y, h h we we also have x and y also engage. Now I'm using plus here because plus operation plus operation because the operation this example is plus. If you're going using just regular group multiplication, you would do x x times y plus x. So it depends on the notation. Typically we use the plus sign. Plus sign if we know the operation is a commutative. Otherwise we just have to use uh, x times h is closed under inverses. So h is closed under inverses. So what does that mean? It means that for every x as h, we have the inverse of negative inverse of x. So it will be negative x also in h. And again, if you were using multiplicative notation, it would be x to be negative 1 plus h. So whenever we have a question that requires us to show something is a subgroup of a group, all we have to do is meet these three conditions. And let's go ahead and prove this one again. let's go ahead and prove this one. And again, this one was purposely relative straightforward. So proof. So first we have to explain why it is non-empty. So we have to think of a simple number that resides in H. You can just pick any integer you want, and then just show its there. Let's use zero. So that note that proof. Note that zero equals 2 times zero is in H. This is because zero is MZ. And when I say zero, I'm talking about this one right here, and that's the end, right? That's your that little end. So this shows that H. It shows that H is not empty. So the first condition is satisfied. So now we have to show H is closed under the group operation. So we'll take any X and Y. So we'll take any X and Y and H. So take any X and Y and H. And then what you typically do in this proof is just write down what it means for elements to be in your set. So this means that X and uh, X and Y that X and Y are multiples of 2. So this is X is equal to 2n 2n and uh, Y is equal to say 2 2m for some integer and 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 an m is in Z. So now we have to show that x plus y is so x and y in also not really good to is to write down it. So then x plus y, and then we know that x is equal to 2n. So we can replace 2n. Likewise, we know that y is equal to 2m plus 2m. Place it with 2m, and we want to write this in a form that will tell us that this element lives inside H. So all elements in H are 2 times an integer. So what we can do is we can factor out a 2. So we can say uh, 2. We can factor out 2 times n plus m, and then here is the uh, here is in 2 to Z. And why is that? Because Z is Z is a group, and it is closed under its group operation. So right, so N and M, N and M are in Z. C is a group, so therefore n plus m is also in Z. So again, you could say that all in these words, or you could write it down a little more formally. So this is because it is an integer, and the reason it is because this is actually a group. So this shows that H is close. H is close under the group operation. So this shows H is close under the group operation, and that key, right? H is close under the group operation because G is right, um, M and and in G, and it's a group. Therefore, the sum is also in G. So it's kind of nice how that happens. Now we have to show that it's close under inverses. Take a new x. So take take any x. Could I use the same one but take another x into z? So x that means x is equal to 2n, uh, 2n our n is in nz. So n now that n is in z and z is group, so since c itself is close under inverses, so this means that this means that negative n is in z, and again this is because z itself is close under inverses. So right, n n is in z, and z is a group, it's close under inverses. So negative n is also in z. I'll see it here because z is close under inverses. So that means let's call let's call it let's call it y. Let's call it y. Y equals 2 times the negative n n is in z. So 2 times negative n must be in 2z na. 2z now we just have to show that uh, to show what's the inverse. So then we will look at x y, I mean x plus y. So so x is 2n, and y is 2 times 2 times negative n. So before we can out 2 can pull out 2, so we get n plus negative n, and plus negative n plus negative n is 0, right? So their inverse is, so you get 2 times 0, so you get 0. So you just uh, look at y plus x. We get 2 times negative n, 2 times negative n, 2 times negative n plus 2n. So this is 2 times, so this is 2 times, and then the negative n plus n. Now going this kind fast, this is 2 times 0, which is 0. So we have x plus y. So we have x plus y equals 0. Um, so x plus y equals 0. 0 is the identity. So this means that y is the inverse of x. So y is the inverse of x, and in particular it's into z. Given any x into z, we have that negative x. It's also into z. So note here, it's not clear that y is 2 times negative n, which is negative 2n, which is actually literally negative. So we can show all the three conditions that it is not empty, close under the group operation, and close under inverses. So this shows that it's a subgroup of G. So this shows it's a big. Uh, this shows that H is a subgroup of G. I hope this video has been helpful to you guys.